Good afternoon, everyone. Happy to be here. Welcome to our talk, Exploiting OPC UA in Every Possible Way. My name is Sharon Brizinov. With me, Noam Moshe. We both are researchers at Clarity, Team 82. In Clarity, we're doing a lot of ICS-related research. So you can see here, for example, our lab in Tel Aviv, where we have a lot of interesting equipment, including PLCs, HMIs, SCADA servers, and we're trying to research all of these products and find vulnerabilities in them. So today we're going to talk about our research into OPC UA, specifically implementations of OPC UA protocol. Throughout the 2 or 3 years, we've researched dozens of different OPC UA protocol implementations, and we discovered many vulnerabilities, around 50 CVEs, and we also developed 12 different, what we call them, attack concepts on OPC UA servers, clients, protocol gateways, basically any product that has support of OPC UA. And throughout these years, we've released open source projects and tools, for example, OPC UA Fuzzer, and today we're also going to share and release a new exploit framework dedicated specifically for OPC UA. And finally, we would like to say thank you to ZDI. ZDI has their own competitions, and they really pushed and emphasized on OPC UA research, and they really incentivized us to research OPC UA in the last few years. And we also got some nice prize money for this. So let's start. We're going to first discuss a little bit about what is OPC UA, cover some protocol stack implementations, discuss the bits and bytes of OPC UA, and then we're going to delve into our research, our vulnerabilities, exploits, and finally share the new exploit framework that we've been working on in the last few years. So let's start with what is OPC UA. What's the problem that OPC UA tried to solve? Now, if we're talking about an industrial process, for example, we have a water tank that we want to keep track of the water level inside of it, we would probably have a PLC with some kind of a logic that keep track of a variable named water level. Now, if we were in the past and we wanted to monitor this process, meaning query the PLC to understand what is the current water level, basically trying to read this variable or this tag, we would need to use the same compatible software that know how to communicate in the specific proprietary ICS protocol with the PLC. And so we were very limited to the type of the equipment that we could have in our factories or production lines. And so OPC UA was kind of invented to solve this, and it became the standard way to exchange data in industrial networks. So now we don't need to have any specific equipment that needs to talk the specific ICS protocol. Instead, we only need to know OPC UA. So all the different products in our factory can communicate in OPC UA, and we have kind of a unified platform to communicate and exchange data on the physical process. So again, for example, if we want to read the water level tag, all we need to do is to do the read equivalent in OPC UA and get this variable. So this was kind of the background why OPC UA created. So OPC UA stands for Open Platform Communications Unified Architecture, and it's a protocol mainly used for data exchange between industrial devices and systems. So in most cases, we have servers which store information about variables and tags, and we have clients that read or write these variables and tags. It's a widely accepted standard for industrial communications, and it's even supported by cloud platforms like Azure and AWS IoT. Now, OPC UA was developed by OPC Foundation around 2006, based on lessons learned from the previous version of OPC DA or OPC Classic. The new version, the OPC UA, became independent platform, which is very scalable and even secure. Now, to make sure all the important aspects of OPC UA are kept, OPC Foundation created a very, very detailed specifications where anyone can find information about the protocol, including the information module, services, for example, how one needs to read or write tags, and also security, for example, how to properly do authentication using OPC UA. Now, to accelerate the use of OPC UA, OPC Foundation created, in the early days, 3 main protocol stacks. So they developed a protocol stack in Java, .NET, and ANSI, and released these protocol stacks. So anyone who wants to start using OPC UA could use them as the base protocol stack for their product. Now, with time, vendor integrated the base stacks and modified some of its code. And today, you can find many, many products, around 500 products, that are using OPC UA, and most of them are based on these 3 libraries. And you can find all these products that support OPC UA in the OPC Foundation website. This is where we looked to understand what do we want to research and how to research it. Now, the problem with these types of products is, as I said, many of them are built upon very specific protocol stacks that were developed in the early days. So the problem is that most products today are heavily relying on the base protocol stacks from OPC Foundation. So for example, if we check the 5 most common products that support OPC UA, for example, OPC UA servers, from different programming languages, from C, C++, .NET, Java, we will see that most of them integrated the core libraries of the protocol stacks released by OPC Foundation and a little bit changed or modified some of its code or added some features, but the base core stayed the same. So obviously, the problem is that if someone will find bugs or vulnerabilities in the core libraries, it will be shared across many different products. So to do this, this is what we wanted to achieve. So to do this, we made a list of all the major OPC UA protocol stacks, servers, clients, basically any product that supports in some way OPC UA. And we started to analyze and categorized different products based on their similarities and base protocol stacks. So for example, if we saw a couple of products that are using the same core protocol stack, or at least what we thought was the same protocol stack, we categorized it on the same group. And so we started to research these groups based on their base protocol stack. Now, before we delve into our research and how we researched these products and protocol stacks, let's do a quick crash course on OPC UA. So in OPC UA, everything is a node. Node is a very strong terminology in OPC UA, and everything is described as node. So for example, our water level variable is also a node, and each node has a type. So in our example, the water level variable will be node with type float. Nodes are arranged inside namespaces. So namespace is kind of a container for nodes, and we can have different namespaces for different purposes. And therefore, nodes can be identified by the namespace ID, NS, and the identification of this node inside the namespace. So every I and NS identify a specific node. Now, the specification tells us exactly how we need to encode and decode nodes over the network line. So in the specification, they say exactly how the namespace should be encoded. For example, namespace should be encoded as byte, and the identifier needs to be encoded as uint16. And this gave us kind of the basic building blocks when we started to research the specification on how should we implement our own packets, our own OPC UA client. Now, in OPC UA, we also have services. Services is our interaction with the server. And we can kind of activate different services that will interact with nodes. So for example, we have a service called read service, where we can use it to read values from different nodes. So if you want to read a variable, like the water level, we can use the read service. We also have write service, like exactly the same for writing values. And we also have something interesting called call service, where we can activate methods in the OPC UA server, and these methods can receive nodes as arguments. And we will see some example for this later. If we go back again to our example, we have a water tank, a physical process that we want to monitor using OPC UA. So in our data model, we will have, for example, our water level variable, which obviously will have a type float. And if we would want to have an HMI to monitor this process, we would configure it to use the read service to constantly read the variable from the OPC UA server. And this is how we will be able to monitor our process using OPC UA. Great. So this was kind of a quick crash course. And now we'll move on to our research methodology. So as I said, we were very interested in researching a lot of different products that support OPC UA. So to do this, we bought 2 Intel NUCs and installed VMware ESXi. We wanted to spin up a lot of different virtual machines. And on each virtual machine, we installed a different product. So we made a very, very long list of different protocol stacks, servers, gateway protocols, clients, etc. Basically, any interesting product that supports OPC UA. And we installed it on different machines and started to research it from different angles. The first angle was to build the basic OPC UA client. From very early in our project, we wanted to have our own client, OPC UA client, that we built from zero, from scratch. And why is that? Because we wanted to have some hands-on experience with OPC UA, so we wanted to build it ourselves. We wanted also to focus on the logic and have a customizable and very tailor-made to our needs. So for example, we configured the client, the OPC UA client that we built, to be very modular and dynamic. So if we wanted to alter and modify and change some of the OPC UA messages throughout their life cycle, for example, when we initiate new session, we could really easily do that and change any aspect of the protocol, from initiating an OPC UA session up to changing specific bits in a very specific OPC UA message. Now, the way we did this is by reading a lot of the specification. The OPC UA specification are really good. They're very detailed. And we also relied on the protocol analysis from Wireshark and other available tools. So once we had our OPC UA client, it was kind of the very basic building blocks for our research, and we could continue and build things above it. For example, one of the things that we built is a network fuzzer that is heavily relied on our client, but also on other frameworks like BlueFuzz. And we ran this fuzzer for a very long time against all the products that we installed on our virtual environment. And we fuzzed mostly 6 services, including read and write of tags, browse service, and other services. And the fuzzer was very, very efficient because it was kind of a passive way for us to keep something running on the background while we're doing other types of research, like manual research. Another thing that we did very early in our research was to also create harnesses and to run some coverage-based fuzzers. For example, we found ANSYS OPC UA protocol stack, so a code base of OPC UA written in C. And we created 2 harnesses for this project, one for AFL and one for a libfuzzer. And we also ran a lot of these fuzzers in the background, kind of in a passive mode. Now, to control all of these fuzzers, both the coverage-based and the network ones, we created a Slack bot to monitor all this process for us. So whenever we had a crash, we got a notification for this. So whenever there was something interesting on the machine, and we had ways to monitor this, we got a notification including the screenshot from the relevant fuzzer. This way, we could easily control dozens of different fuzzers, from network ones to coverage ones. We had all the fuzzers running in the background, and now we wanted to move on to do some manual work. So we started to look for esoteric features and complex features in the OPC UA specifications. And we mainly tried to understand what developers will overlook. So let me give you, for example, if we're talking about OPC UA, it has a very strict header message. So in the header, there is a flag saying is final. Now, OPC UA supports chunking of messages. Let's say we want to send a very, very long message. We can divide it into different chunks and send a chunk in each packet. Now, to make sure the server is aware that we're sending a very big message in chunks, we need to notify when is the last chunk. And we have this flag saying that if it's the last chunk, we will say this is the final using the F letter. So we were thinking this is a very nice feature, but maybe it can be abused in some way. So what happens if we just keep on sending chunks without ever sending the final chunk? What would happen? So we had these types of questions in our mind while reading the specification. We wrote everything on the side, and we continued. So let's give a couple of examples to vulnerabilities that came up through our research. And we'll start with denial of service. Obviously, denial of service is very interesting when we're talking about physical processes, because having a denial of service in a live process could mean some disruption and maybe catastrophic results. So obviously, shutting down OPC UA server means there is no analytics, no monitoring of the process, and maybe something bad will happen. So this was a very valid case, and it was interesting for us to research. And to do this, we made a very long list of all the possible ways that we can achieve denial of service. For example, what happens if the server will crash due to uncontrolled memory management? What happens if there will be a threads deadlock? And it was important for us to make this list because these were the things we tried to focus on when we did code review and when we did reverse engineering work. We tried to focus on these types of scenarios when we were talking about denial of service. Now, we came up for each category, by reading the specification and doing reverse engineering work, we came up with a very long list for each category of potential attacks that could influence not just one OPC UA protocol stack, but many of them. So, for example, I discussed the final flag. We developed an attack called chunk flooding, and it goes like this. We have the OPC UA message header, and we have the chunk type. And the chunk type is one of the flags within the OPC message header. And usually, if it's a chunk, it will be C. And if it's the final chunk or a single chunk, it will be F for final. And if we look at the code, for example, a very popular protocol stack, OPCUA.NET, we can see that the server is looking for this byte to be F to finalize the message. So if it's not F, it means that we're in the middle of sending a very long message, and it needs to keep on receiving messages. So by reading the specification, we understood maybe we can abuse this by sending a lot of different chunks, and without ever sending the final message, what happens to the server by feeding it with more and more chunks? Obviously, it will allocate more memory, and it will read more chunks, but there were no limitation for this because, again, developers probably overlooked it, and so finally the server crashed. And again, this was not a one-off. It was a common vulnerability across different protocol stacks. And by abusing these protocol stacks, we were able to exploit and crush many products that relied on these base protocol stacks. Another interesting denial of service concept is method calling from a dead session. And this is part of a use after free category. And it goes like this. In OPC UA, we have a way to configure methods within the server. So we can program a specific method that we can remotely call it from a client. Now, this method can receive arguments as nodes, and we can activate it remotely, invoke it. And when we read the description for methods in OPC UA, we noticed something interesting. So we noticed that if method is invoked from the context of a session and the session is terminated for some reason, the result of the method execution cannot be returned to the client because the session is gone. So obviously, we ask ourselves, did all the developers really implement this correctly? What happens if we will send a very, very long array in OPC UA containing method calling, so basically asking the server to execute 255 very complex methods, and then immediately terminate the session? What will happen next? And this is exactly what we tried. Using our client, it was very easy to configure this type of scenario. So what we did is we sent a very long message with an array of methods, and we sent it to the server, waited for the server to start processing each method. And when it reached to the middle of the methods, we immediately disconnected the client, so terminated the session. Now, obviously, when the server finished to process all the methods, it should have checked if there is an active session, and if so, return an answer, and if not, just discard the result. But instead, the server tried to dereference a session which was not exist, and we got a null dereference. So again, this is another type of concept we developed based on reading the esoteric features of the OPC UA specification. Okay, denial of service is interesting, but not cool. So let's move on to remote code execution scenarios. Obviously, remote code execution is interesting because we are not crushing the server, rather executing code on it. And if we have code execution on OPC UA server, we can modify the results, fake the results, delete the results, or even crush the server. So remote code execution is obviously very interesting, and it was one of the vectors we researched. Now, we decided to research one of the servers was PTC Kepware. It's a very popular OPC UA server. One of the actually industry-leading OPC UA server used in the biggest manufacturing lines, oil rigs, wind farms, etc. It's a Windows-based server, and they have their own custom OPC UA protocol stack. The OPC UA logic is found in the server runtime service, and most of it is what we researched. Now, I told you about our OPC UA fuzzer, and we, as I said, ran it for quite some time. And one day we got a notification from our bot that we got a crash. Immediately we're very skeptical because sometimes we're getting false positives. But we decided to research this anyway. And by the way, this is the real image of the crash that we got from our bot. And we started to analyze it, and we saw there is something related to string processing. So we started to analyze the crash, and we saw something is off with the way that Kepware, the OPC UA server, is processing strings. Now, strings in OPC UA is very interesting because it's part of the OPC UA specification, so they really specify how strings should be encoded and transferred over the line. In OPC UA, strings are encoded using UTF-8. And we have strings almost everywhere. So for example, if we have our tank water tank, you'll see strings in this example, for example, the name of the water tank, the location of the water tank. And we can see it both in the OPC UA server and using Wireshark, for example, you can see here, we have the location of the tank or the name of the tank. Now, the interesting part is that Kepware was trying to convert the string from UTF-8 to UTF-16, and it failed. UTF-8 is the way that strings are encoded when we're transferring the data over the line, but it tried to convert it to UTF-16 because this is how Kepware kept strings in memory. So obviously, we started to research and explore these functions in the Kepware server, and we discovered something interesting. There was a bug in the process of converting from UTF-8 to UTF-16. Now, to understand this, we need to understand real quick how UTF-8 encoding works. So usually, we have a conversion of 1-to-1 if the ASCII, if the byte is less than 80 hexa. But if we have a funny-looking A here, it won't be converted to 1-to-1, but it will convert it to 2 bytes. So we have a symbol, the funny-looking A, and it will be encoded as 2 bytes instead of 1. Now, when Kepware is trying to parse a string from the OPC UA server, it will try to understand how many symbols do we have in the packet, and it will try to convert it to UTF-16. So let's give a quick example. Let's say we have this string, and we're sending this over the line. We have AA, and finally, funny-looking A. Now, when Kepware will try to understand how many symbols we have here, it will see that we have 1 symbol, 1 symbol, 1 symbol, and then 1 symbol that has 2 bytes. So when it will try to calculate how much memory it needs to allocate, it will calculate it as 4 symbols, but the 4th symbol has 2 bytes long in UTF-8. So it will reach to the null terminator and stop over there. And eventually, it will try to convert from these bytes to UTF-16. So what happens if we're sending something that is not correct UTF-8? Well, we're sending a malformed UTF-8. So let's give another example. 41 is 1 symbol, capital A, but it's also 1 byte. And we have it again, so 1 symbol, 1 byte, and 1 symbol, 1 byte. And now we have C3. So in Kepware, there was kind of a bug that when it reaches some areas, it will automatically try to deduce how much memory it needs to allocate. And if it reached, for example, C3, it automatically assumed there are 2 bytes. So what happened is it reached what it thought was a single symbol with 2 bytes. So it skipped the next byte, which in this case was a null terminator, and started to jump in the heap. So basically, we were able to skip the null terminator that stopped the string, and it started to count more symbols over the heap until it reached another null terminator. And this is how we were able, basically, to leak the heap, because we skipped the null byte, so the string was not terminated where it should have been. Now, we were able to leak data using this primitive, and it's very cool that our father found it. And actually, the father found other bugs, but we were able to leak data using this by reading different tags. So as I said, in OPC UA servers, we can read variables. So we just tried to read variables with C3 at the end, and we were able to leak more data than the server should have given us. Now, we were also able to convert this not only by abusing the read tag functionality, but also by abusing the write tag. So we tried to write variables with C3 at the end of their name, and we were able to overwrite data in the heap. So we now had 2 primitives to work with, read, out-of-bound read and out-of-bound write, and we used the read for leaking pointers to defeat the ASLR, and we used the out-of-bound write to construct our rope chain, and finally get an RC. So finally, this is exactly the exploit that we ran in Pwn2Own 2022. And how it worked is, first we leaked data from the heap, and then calculated from the pointers that we leaked the base addresses for all the libraries that we needed for our rope chain, constructed our rope chain, and finally triggered the remote code execution. Thank you. So using this bug, we're able to get remote code execution in Pwn2Own, and it got us to 20K. No?
Thank you. OK, so Sharon just showcased to you some RC vulnerabilities we identified in OPC UA servers. However, next thing we aim to do is actually exploit a different kind of machine in the OPC world, it being actually exploiting the OPC UA clients. So let's talk about the scenario right here. If, let's take, for example, the water level example we've showcased all slide long, we have an OPC UA client connecting to a malicious OPC UA server and trying to read a tag from it. We thought to ourselves, what would happen if somehow we would return a malicious tag and exploit some kind of vulnerability in the OPC UA server? Well, that is exactly the kind of vulnerability we exploited in the Pwn2Own competition last year, in 2023, where we exploited two different web-based OPC UA clients, it being Inductive Automation Ignition and Softing Data Feed Edge Aggregator. Now, one thing these two clients had in common is that they were both web-based, meaning the clients, the users, actually authenticated to the web server and actually acted as an OPC UA client over a web browser. So because we were in the realm of web browsers, we thought to ourselves, what is the obvious kind of vulnerability type we can exploit? It being an XSS vulnerability in the read, write, or subscribe method and services. So for example, if the client would connect to our rogue OPC UA server and try to read or write a tag, we would attack it somehow using an XSS payload. So this is exactly how it looks. We have the client connecting to our server and requesting to read a tag. Now, when it tries to read a tag, we simply say, yeah, sure, here is your tag. However, instead of returning a float or a basic string, we will return an XSS script, which then the client will take our XSS script and simply insert it into its DOM in the browser, which will trigger an XSS vulnerability and allow us to basically execute arbitrary JavaScript code on the OPC UA client browsers. Now, this is exactly the kind of vulnerability we actually managed to exploit in both Softing, as you can see here, and in Inductive Automation Ignition, where we're able to execute arbitrary code in the browser of the user. However, that's pretty cool. We can now maybe recall the user or showcase some kind of weird interface in the DOM. However, our goal was not only to manage to change the DOM somehow, but instead we wanted to leverage this XSS vulnerability into achieving a remote code execution on the client by chaining different vulnerabilities along with the XSS vulnerability and actually managing to exploit the OPC UA client. Now, because we were talking about specific vulnerabilities, the two vulnerabilities we exploited in both in the Ignition and Softing were different, so let's go over them real quick. So first thing first, we are able to exploit and execute arbitrary JavaScript code, and because we are running in the browser of an authenticated user, we are now authenticated as well, meaning we are able to invoke arbitrary functionality on the server itself. Now, because we are authenticated, we are able to perform different kind of actions. And in the case of an Ignition server, the obvious thing was, of course, uploading a new project. Now, when you upload a project to Inductive Automation Ignition, you are able to actually specify something called a gateway event. Now, gateway events are actually scripts. As you can see here, it is a script written in Python. And whenever a specific event occurs, our script will be executed as a callback, allowing us to basically execute Python scripts. Now, we chose to implement an on-schedule event, meaning it will occur every set number of seconds, meaning we're able to simply execute arbitrary Python code and actually manage to exploit and achieve remote code execution on the inductive automation ignition gateway. Now, in the case of softing, now we actually changed multiple different vulnerabilities in this case in order to achieve this remote code execution, getting us the ability to basically attack any different kind of inductive automation ignition servers. Now, in the case of softing, our exploitation technique was a little bit different. There was no some kind of a project, but instead we had the ability to perform a backup and restore procedure. Now, what's a backup restore procedure, you might ask? It is basically the ability to restore the configuration of the server to an old state of the configuration. And whenever we would do that, we would actually upload a zip file for the restore operation, and our zip will be opened, and all of the different configuration will be restored. Now, since it was a zip file, we thought to ourselves, maybe there is a zip sleep vulnerability, allowing us to actually escape the intended directory and basically achieve a arbitrary write primitive on the softing server. And that is exactly what we did. So we simply wrote a malicious SO that will execute code whenever it is loaded and perform the backup operation restore procedure. And whenever we did this, we gained the ability to execute code on the softing server, giving us another RCE vulnerability. Okay, so the whole OPC UA procedure and research we've conducted was pretty extensive. So we thought to ourselves, yeah, we actually managed to identify and release over 50 different vulnerabilities and actually identify attack concept, meaning one concept, one kind of attack and vulnerability that could affect even dozens of different OPC UA products. So we took this entire knowledge and this entire client and code base and POCs and actually aggregated it into our own OPC UA exploitation framework. This framework actually contains most of our different work over the years, including the POC code and all of the exploits for the different OPC UA gateways, servers, and clients. So feel free to scan the receipt, to scan the QR code. Cool. So this framework will be accessible from our GitHub page. Feel free to use it on your environments for, of course, only ethical reasons, to test it against your OPC UA products, if you are an OPC UA vendor, etc. And in this framework, we actually have the POC code and documentation for all the different OPC UA exploits we developed over the years, including the ones we talked about today, including the chunk flooding, of course, different vulnerabilities of different OPC UA products, our capware exploit, etc. It is a very, very extensive exploitation framework, and we believe it can be used for good. We actually opened a Slack coalition with different OPC UA vendors in the last few months, giving them early access to test their products against the different vulnerabilities we are going to showcase in our exploitation products. And a lot of different vendors basically got to validate and test their product against the different exploits and techniques we developed in the last few years. And of course, it is very extensive and contains all of the different exploits. So let's summarize everything up and talk about all of the research we've conducted over the last 3 years. We actually participated in 3 different pwn-to-own competitions using both our clients and our exploitation framework. And actually, during this year, we won the Master of Pwn Award, actually exploiting most of the OPC UA clients and servers. We found dozens and dozens of different CVEs in many different kinds of products involving OPC UA, including gateways, servers, clients, etc. And we actually managed to develop what we call techniques, meaning one exploit that works against multiple targets with minimal changes. We believe our OPC UA exploitation framework can be used for good and should be used to test your environments and your different OPC UA products. So feel free to download it, clone it, and of course contribute to it because it is open source. Feel free to add support for your different products. So thank you everyone for attending our talk, and if anyone has any questions, feel free to come up to the mic and feel free to ask anything. Thank you very much.